right, thanks for coming back to the final session. And I won't be talking about God too much in this talk, although what I do say in the talk is in part motivated by the kinds of issues that we've been talking about. In particular, I'm sure you both know these two quotes. Nietzsche, of course, famously pointed out that God is dead. He was not, as many people casually think, celebrating the fact that God was dead. He was worrying about it, right? Now we have lost this grounding for much of our sense of value and morality in the world. What are we going to do? How are we going to comfort ourselves? And then Steven Weinberg, another famous existentialist philosopher, points out that the more we understand about the universe, the less purpose there is inherent in it. It just seems to be mindlessly following little laws of physics. So what I want to do, for 49 of my 50 minutes, I will be talking about physics, or maybe it'd be better to say a physicist version of philosophy. And then in the last 1 minute, I will explain how the meaning of life comes into physics. So let's start. Here's some physics. This is what we thought about the fundamental ingredients of reality circa 1935. The beginning of what we now call particle physics. We had discovered that there was the structure of the atom. There's a nucleus inside, electrons on the outside, governed by the rules of quantum mechanics. And the nucleus was made of a combination of neutrons and protons, held together by some mysterious nuclear force. And the electron, which was circling around, was held to the nucleus by electromagnetism. And the whole shebang was being pulled down by gravity. Everything, according to gravity, pulls on everything else. And you would have been forgiven, I think, by at least wondering whether or not we were close to being finished. I know that before quantum mechanics came along, people speculated we were close to being finished. But out of these ingredients, it was seemingly possible to make everything that we see around us. We were not finished, of course. We've added new particles, but the basic structure has remained pretty much the same. We not replaced, but we found a layer of structure underneath the protons and neutrons. They are made of up and down quarks, and those are held together by what we call the strong nuclear force. The electron is still held to those by electromagnetism. That hasn't changed. There's also something called the weak nuclear force, obviously, if there's a strong nuclear force. And the weak nuclear force is important. When you fuse protons together and a neutron is created, you spit out a neutrino, and that's, for example, what makes the sun shine. This is a phenomenon that is very important where I come from in Los Angeles. Here it's less crucial, but there's a big thing in the sky that rains down heat and light onto us through the weak nuclear force. And gravity is still there, and in the background you can't see it very well, but there's something called the Higgs field, which we finally found direct evidence of just in this July. So here's the news. Oh, and of course, these up and down quarks, electrons, and neutrinos make up a generation of particles. That pattern is repeated 3 times. There's 2 other generations that take the same form. And of course, they all also have antiparticles. So now we have this picture of the fundamental ingredients of reality. And I think that we are in a much stronger place to make a claim that sounds like the claim we shouldn't have made in 1935, but you need to listen very, very carefully to what the claim is. This theory that is encapsulated as fundamental ingredients on the previous slide is the standard model of particle physics, plus general relativity, Einstein's theory of gravity for the gravitational force. It gives us a working theory of not all of reality, but all of the reality that we witness in our everyday lives. So all the parts of the universe that were not contained on the previous slide, you need to be a physicist or an astrophysicist to come across. You need to have powerful telescopes or microscopes. Everything that you witness in your day-to-day walking around is encapsulated by this theory. It is internally complete and coherent now that we have that Higgs field. We don't have any loose ends that say I can't make a prediction unless I know something new. It is uncontradicted by any experiment ever conducted here on Earth. We know this theory is not right because it doesn't include what we call dark matter, for example, much less explain the center of black holes or the beginning of the universe. But here on Earth, try as we might, we have not done an experiment that has ever contradicted the standard model of particle physics plus general relativity. Now, that doesn't mean that it's right, but I'm going to argue that it's pretty close to meaning that it's right. In fact, that is point 3, and this is the underappreciated point, that as far as the physics underlying everyday experience is concerned, it's not just that I have a set of particles and dynamics that seem to be compatible with you and me and the table and the sun and the moon and the stars. But we have excellent evidence that there is no new physics required or allowed in that regime, in the regime of everyday stuff. Of course, once again, there is more physics ultimately, but whatever new physics there is, it will not play an important role in you and me and the stuff going on in this room or here on Earth. So to put it a little bit more quantitatively, here is the one equation that suffices to explain everything you've ever seen, unless you're a professional physicist or astrophysicist. I'm not going to go through all of the details here, but I can give you the general flavor for what's going on. This is the quantum mechanical amplitude to make a transition from one configuration to another. And this part of the equation is basically quantum mechanics. This is, my laser pointer is dying, quantum mechanics is failing me. This is the Feynman path integral over all possible trajectories that connects the two configurations. This little bit is space-time. You integrate over all positions in space and time. This little bit is gravity. You can see why people think that general relativity is such a beautiful theory. It takes up very little space on the transparency. All the other forces of nature are contained here. They're what we call gauge forces, strong and weak nuclear forces, and the electromagnetic force. Here is matter. This is the ugly bit that is protons, neutrons, electrons, quarks, etc., muons. And this little bit is the Higgs field that allows mass and breaks the symmetries in empty space. And so you can also see why the discovery of the Higgs field was so important. It's a substantial fraction of the theory that we need to explain everything in the universe. So the claim I want to make about this equation is that 1,000 years from now, this will still be the equation that describes the particles that make up you and me in our everyday experience. We will not discover, even in the future, that there's some other field out there that plays a really important role in, for example, human consciousness. I'm going to make that claim, and I'll try to justify it the best I can. And the reason why I need to be careful about it is because it sounds like I'm making the same kind of claim that you might have worried about people making 100 years ago or 200 years ago, where they said, you know, physics is practically done, we just have to dot some I's and cross some T's. But this is a different kind of claim, so I want to be very specific about it. And the reason why I can make this claim is because this theory is based on quantum field theory. So if a physicist 150 years ago had said, you know, we understand mechanics, we understand classical dynamics, Newtonian mechanics, that seems to be enough. That seems to be a robust framework in which physics happens, and therefore I predict that 1,000 years from now we'll still be using Newtonian mechanics as their fundamental workings of reality, even though the details of the dynamics and forces might change. And that physicist would have been wrong, obviously, because quantum mechanics came along, not to mention relativity. So the difference with our current framework of quantum field theory is that if quantum field theory is correct in a certain regime, Newtonian mechanics is correct in a certain regime, right? I mean, we don't need quantum mechanics to fly a rocket to the moon, for example. Quantum field theory, unlike Newtonian mechanics, tells us very precisely what regime it is valid in. It gives us a delineation of where the theory is supposed to work and where it's not supposed to work. You can draw that line. And it turns out that in practice, drawing the line around the quantum field theory I drew on the previous slide includes all of our everyday experience. So let me explain that a little bit more. You might have heard I know it's a mixed audience, you've probably heard about somewhere in your physics education, are things fundamentally particles or are they fundamentally waves? And if you're like me, when you heard that, you never really heard what the answer was to that question. So I will give you the answer. It's waves, okay? That's the answer. Stuff in the universe, the fundamental ontology of reality, are quantum fields. And the reason why the particles come in is because the quantum part of that implies that when you look very carefully at the fields, they resolve into particles. Not because they are particles, they are fields, they are waves, they are smooth, continuous things filling all of space. But quantum mechanics says that what we see is not what there is. We see things in a different way than the unmediated reality when we're not looking at it. So if you look at the light from this light bulb, if I walk away from this light, if it gets further and further away from me, it becomes dimmer and dimmer. And if I had perfect eyeballs, it would stop becoming dimmer at some point, and instead it would start becoming intermittent. It would start flashing rather than diminishing in brightness. And what that would mean is I was detecting the individual photons being emitted from that source. But what quantum field theory says is it's not individual photons that are being emitted, it's a quantum electromagnetic field, and my eye is detecting them in discrete packets of photon energy. And that works not just for photons, not just for gravitons, but for every particle that you've ever heard of. Electrons are vibrations in an electron field. Neutrinos are vibrations in a neutrino field. Everything that we are made of is a vibration in one form of quantum field or another. And it was Ken Wilson, a Nobel Prize-winning physicist in the late 60s, early 70s, who told us how we should think about quantum field theory, which is that we should organize it by energy or equivalently by length scale. In quantum mechanics, high energy means short wavelengths. So as you go down in distance, you go up in energy. And then he says if you're thinking about prospective new quantum fields that you might want to add to your ontology, there's, roughly speaking, two things you need to tell me about them. One is it heavy, massive, or is it light? So what is the mass of this field? And that's because the more massive a field is, the harder it is to push it across a long distance. So heavy fields tend to give rise to short-range phenomena. The weak interactions of particle physics only happen over very short ranges because they are carried by these very massive bosons, the W and Z bosons. If you have a light field, like the photon is massless, it will give you a force that extends essentially infinitely far. And then the other thing you need to tell me is how strongly that field interacts with other fields. If it's weakly interacting, it'd be hard to detect. If it's strongly interacting, it'll be easy to detect. So the rule is that, roughly speaking, things that are light, that extend over long distances, or strongly interacting are easy to detect. They are accessible to our experiments. Whereas if they're either very weakly interacting or very short range and heavy, then they are inaccessible to our experiments. That's why we need to build the Large Hadron Collider to make the Higgs field. It is not so weakly interacting, but it is very, very heavy. And therefore, we have a classification that matches on to our, in the United States, our former Secretary of Defense, Donald Rumsfeld, proposed an ontological classification scheme by which there are known knowns, known unknowns, and unknown unknowns. So here they are on this plot. We know where the known knowns are. They're fields that are long range and or strongly interacting. We know where the known unknowns are. They are either heavy and short range or weakly interacting. The unknown unknowns, and here's the crucial point, are not on the plot. If quantum field theory is right, we know where the unknowns are. Of course, quantum field theory might not be right. As a scientist, you have to open yourself to the possibility there is some dramatic violation of these fundamental things, just like Newtonian mechanics would have been right. But the lesson here is that under the assumption that quantum field theory works, and it's the best tested scientific theory framework we have, then you can draw the line and see here's where I know all the unknown stuff must be lurking. It can't be up here or I would have detected it. Let me be a little bit more specific about that. There's something called crossing symmetry in quantum field theory, which relates different kinds of fundamental processes. So imagine there was some new particle. Imagine that human consciousness relied not just on electrons and protons and so forth, but also on new Zilbot particles that came in and interacted in little consciousness waves. Okay? Let's imagine someone wanted to believe that. So what that would mean in the level of quantum field theory is here's, a proton or an electron in your brain. There's the Zilbot, it's a new particle, and there's some new interaction that lets these particles interact with each other. And we assume that the Zilbot is either ambient, it's floating around, or it's created somehow, but the interaction is strong enough that it affects how we think. It's the consciousness particle, okay? Imagine that was a hypothesis. And this is a Feynman diagram saying how processes go on as a function of time. That these two particles bump into each other, they interact, and they go out the other way. And to a physicist, this diagram is not just an interesting cartoon, it is a useful calculational tool. This diagram corresponds to a number, which tells us how probable this process is. And it's a fundamental rule of field theory that I can take this diagram and rotate it by 90 degrees, and I get another diagram with the same amplitude. So all I need to do is turn this on its side so that the protons come in, or a proton and antiproton. They will interact via the same interaction and produce Zilbot particles. So the point is that if this new particle, this new interaction were strong enough to actually have an effect on what's going on in your head, we would have made this new particle directly in particle accelerators a long time ago. Any new particle that could possibly be relevant to your everyday life, we would have made in a particle accelerator, and we haven't. This is a fundamental consequence of the underlying architecture of quantum field theory. So you might say, can there be new particles we haven't yet detected? And of course the answer is yes. We think that whatever makes up the dark matter is a new particle we haven't detected, but we know the ways we could possibly hide it. That's the crucial thing. Either it's weakly interacting, too heavy to create, or too short-lived to actually detect it. And in any of those cases, it would not be relevant to the everyday physics we have around us. That's why we need to make something like the Large Hadron Collider to actually produce these new particles. Unless you have a Large Hadron Collider in your pocket, none of these new particles are going to be important as you walk around the streets of Oxford. Likewise, could there be new forces of nature? Could I bend spoons with my mind using some new force other than gravity, electromagnetism, and the nuclear forces? Well, the answer is there can be new forces, but they either need to be very weakly interacting or very short-ranged. In other words, I cannot bend a spoon with my mind other than telling my mind to use my hands to bend the spoon. There's no new force of nature that extends from my brain to the spoon in order to bend it because we have ruled out all the possibilities. And in case you think I'm just whistling there, this is an actual experimental program. Here are the data that actually rule out new forces. This is the range of a new force that you might try to invent, the extent to which it passes through space, from a meter to many, many kilometers. And here is the strength relative to gravity. So this is, 10 to the minus 6 means this is 1/millionth the strength of gravity. And gravity is a very weak force. So being a millionth the strength of gravity is really, really, really weak. And this plot is telling you that at the range of you could extend this, I just got the wrong plot, but at a meter or a decimeter, so about this distance, the strongest possible new force is 1/100,000th the strength of gravity. That is not enough to bend a spoon with your mind, which is that distance over which you have to go. So we know that as long as quantum field theory is basically right, there are no new forces in particles relevant to your everyday life. So the laws of physics underlying the experience of our everyday lives are completely known, unless we're dramatically wrong about quantum field theory itself. Now, all the colored words here are important. Obviously, black holes, dark matter, we don't understand, but also underlying is a very important word. I'm not saying that we understand biology or chemistry or economics or anything like that, but I do think that whatever understanding we get of those phenomena better be compatible with the underlying laws of the Standard Model plus gravity. So since I'm certain from personal past experience that this will be misunderstood, I'm just going to say the same thing over and over again. Fundamental laws do not mean the interesting laws. The fraction of professional physicists who spend their time studying this fundamental kind of particle physics is very, very tiny even within physics. It is certainly not everything interesting within science, so don't claim that I'm saying anything else. It certainly doesn't mean useful. I am certainly not trying to say that the right way to think about chemistry or biology is to start with the standard model of particle physics. That would be crazy. No one would even give you a grant to do it. Lower level knowledge is often completely useless at the higher level. In fact, this is why when the United States wanted to build the superconducting supercollider, a proposed alternative to the LHC in Switzerland, one of the set of people who testified against this large particle accelerator in front of Congress were other physicists who don't work on particle physics. Because they said, this is just going to discover new particles. Those are utterly irrelevant to those of us thinking about superconductivity or atomic physics or so forth. Deriving a higher level theory from a low level theory is probably not the way to go, usually. I'm going to talk a lot about higher level emergent theories, and whether or not you can get them by actually starting with a lower level theory and massaging it using math is irrelevant to the underlying ontological relationships between them. And finally, again, we don't understand plenty of things about fundamental physics, but there is a regime in which we do understand it. That is the claim that is being made. Okay, so despite the fact that there is all sorts of lack of clarity in the relationship between the lower level theories and the higher level theories, there are some consequences we can directly get. No spoon bending with your mind, just on the basis of what we know about quantum field theory today. Astrology is wrong. The position of Saturn in the sky on the day you were born cannot possibly affect your later personality in any interesting way. Why? Because we know what forces could possibly extend from Saturn to your birthplace. They are either gravity or electromagnetism. Gravity is far too weak, and the electromagnetic force of Saturn is swamped by other various electromagnetic fields being created by other things. We know astrology is wrong without doing complicated double-blind studies or anything like that. It violates the fundamental laws of physics. And we can be more profound than that. There is no life after death, if this is the right theory of physics. There are no fields there in that list of ingredients that could carry the information about the human mind or the human soul outside the body after it has disappeared. Because there's just no way for that, we know what the universe is made of. We know that there's electrons there, there's protons and so forth. There's no other particles that information can be transferred into. Of course, if you violate quantum field theory and you want to go beyond a purely materialistic description, then you can do it, but that's what you would need to do. There's no new physics to be discovered that allows the soul to exist after the body is gone. Okay, I'm glad you agree with all that. So now let's talk a little bit more about the relationships between these different levels. And I use different words to describe what I mean by a theory on a different level. You can call it a model, a vocabulary, an ontology, a story, whatever you want to call it, a way of talking about reality in a deep way. And we all know this cartoon, right? That particle physics underlies chemistry, which is under biology, which is under the social sciences. And we all know how problematic this cartoon is. There's a lot of ways in which this is not the right way of thinking about things. I'm going to try to tease out what some of the allowed ways of thinking about this are. So the questions that are confronting us are, what does it mean to say something is emergent? What does it mean to say that one theory depends on another one in a certain way? So I like to, just like John was saying, pick out something that is simple and understandable, right? So we can understand something absolutely and then use the lessons from that to understand other things. So there's two cases which we really understand what's going on. One is when two different theories sound very different, but in fact are completely equivalent to each other, or describing exactly the same underlying phenomena. And that's actually very rare, but it's sometimes we get lucky. More common is when one theory is a coarse graining of another theory, when one theory is just trying to capture some subset of what the other theory is talking about. So just so you know how dramatic this can get, here is a very celebrated recent example of two theories that look very different, yet encapsulate precisely the same physics. This is what physicists call a duality between two very different theories. This is the ADS-CFT correspondence, or more generally called the gauge-gravity correspondence. And you don't need to know what any of the letters or words mean. What it means is there's two different theories. One of these theories is gravity in a five-dimensional space-time with certain boundary conditions, and a certain kind of gravity with certain matter fields, supergravity to be technical about it. So gravity in a five-dimensional universe. This theory is a theory without gravity. It's just non-gravitational quantum fields, particles and forces, in flat space-time in 4 dimensions. So these two theories could not look more different. One of them has gravity, one doesn't. One is in 5 dimensions, one is in 4 dimensions. But there is a dictionary that translates precisely between them. It is necessary highly non-local, this dictionary, because there's different numbers of spatial dimensions in the two of them. But there are two different ways of describing precisely the same physics, two different stories that we could tell about that underlying reality. The more common case is when one theory is a coarse graining of another theory. So the classic example in that case is atomic theory or kinetic theory, a theory that the air in this room was made of molecules bumping into each other. And then a theory of fluid mechanics or thermodynamics, a coarse-grained theory in which we ignore the individual atoms and molecules and talk about fluids with a certain pressure and velocity and density and so forth. And the nice thing is that there are a large number of equations because there are a large number of individual molecules in this room. If you wanted to talk about the air in this room molecule by molecule, you need a very powerful computer in order to do that. Over here, you reduce that huge number of equations to a very tiny number of equations. That's cheating a little bit because these equations are equations as a function of space, but if you sort of discretize space inside the box into a million or a trillion lattice points, then you still get a tremendous efficiency of description. And the amazing thing about this is that this theory exists and it works. That you can ask a question in this higher level theory and get an answer without ever knowing the details of what is going on. It is a feature of reality that we can ask questions about it and get useful answers while knowing very, very, very tiny fraction of what in principle there is to know about that underlying reality. So it's this kind of relationship that I want to discuss in a little bit more detail. So how do theories relate to reality? And again, this is my cartoonish physicist version of what is a long discourse in the philosophy of science, but let me just, so you know how I'm roughly thinking about it. So here's reality. I call reality R. Here is a theory that is supposed to capture some important aspects of reality, but not the whole thing. What does that mean? That means that I think of reality as, it has a set of states that the universe could be in, and those states evolve with time, perhaps, and those states have some relationship to each other. And there is mathematically a map from this space of possible states to this one that takes a subspace. So there's some subspace of all the possible instantiations of reality that are described by this theory. So for example, the standard model of particle physics doesn't work if you try to collide two particles with Planck scale energies. That is not in the subset of reality that the theory is trying to describe. Within that map from reality to the theory, it is generically many to one. There are many, many individual varieties of reality that might look exactly the same by the lights of this theory. If this theory is thermodynamics, there are many different arrangements of the molecules in this room that have the same density and velocity and pressure and so forth. And importantly, phi preserves the structure of reality. That's what it means to be a successful theory. If one state here evolves under time evolution to some other state, then if you map those two states into your theory, then one evolves into the other one. It's actually tracking how reality really behaves. So that's just a cartoonish way of saying what scientific theories try to do. How do you relate to different theories to each other? So what it means that one theory is sort of emergent or coarse-grained version of another theory is that they both try to talk about little subsets of reality. And in general, these relationships could be very, very complicated and different and overlapping in some places and non-overlapping in other places. But in the particular case where we're lucky and one theory is a coarse graining of another theory, what we mean is that the little subspace of reality that theory U is trying to describe is a proper subset of the place where theory T is trying to describe it. And the map from reality to theory U can be decomposed by saying, let's take reality, let's map it to theory T, and let's map some subspace of that into theory U. So in other words, it sort of doesn't matter whether we think of theory U as a theory of reality, or whether we think of it as first a coarse graining of theory T and then theory T as a theory of reality. The fact that this composition works is the mathematical way of saying both of these are good descriptions of reality in their appropriate regimes, and theory U is a good description of theory T in some appropriate sub-regime of that. So the reason I'm setting this up is to try to emphasize some of the consequences, the implications of these relationships, which are not always completely obvious. One that is very important is that you may have many different, more fundamental theories, lower level theories, that give you exactly the same higher level theory. This is not just conjectural, this is absolutely true in quantum field theory. You can say exactly how different theories relate to each other. And they're what are called universality classes. You can say that many different microscopic descriptions have the same macroscopic behavior. This is the reason why Phil Anderson argued against building the superconducting supercollider, because he says it doesn't matter what quarks and leptons you discover, my theory of high temperature superconductivity is going to be unaffected by that. And it's kind of sad that this is true, because the standard model of particle physics that I gave you, we are never going to discover the correct theory underlying the standard model just by studying the standard model really precisely. because there are many possible, what the particle physicists call ultraviolet completions of the standard model that give you the same low energy physics. That's just a fact about how the theories hold together. So in that sense, you could say that this higher level theory is autonomous. You don't get the higher level theory, thermodynamics or superconductivity or whatever, by thinking about, well, what is the right lower level theory and then coarse graining. You can just invent this theory all by itself without ever knowing what the lower level theory is. That's a remarkable, very useful feature for scientists about reality. Another feature is that the higher level theories might seem to have very different fundamental characters than the lower level theories. You cannot naively say that because the lower level theory behaves in a certain way, the higher level theory is also going to behave in that same kind of way. So for example, my favorite example, once again the last Oxford mini course, is the relationship between atomic physics at the lower level and thermodynamics at the higher level. The atomic physics is purportedly completely reversible. There is no directionality to the interactions. There is no arrow of time. In the higher level theory of thermodynamics, there is an arrow of time. There is the second law of thermodynamics. And why is that true? It's because this map phi that takes you from the lower level to the higher level only applies to certain cases within the lower level theory. In particular, we say that there is a past boundary condition. If this is the evolution within your lower level microscopic theory, what we call the past hypothesis is the statement that when you're looking at this intermediate moment in time, you don't put a uniform measure over all of the states that are compatible with your observations. You conditionalize on them coming from a particular low entropy boundary condition in the past. So by only referring to a subset of the possible behaviors at the lower level, this deep feature of irreversibility in an arrow of time can appear at the higher level even though it wasn't there at the lower level. And this could, in principle, I think this is a fact about how reality actually works. In principle, many things like this could happen. The character of the lower level theory might not be immediately reflected in the higher level theory. So for example, you might ask yourself, could you have a higher level theory which is teleological, which seems to be goal-directed rather than simply instantaneously evolving? The standard model in general relativity, the best theory we have of fundamental physics, has in it absolutely no teleology or purpose or any future directedness in any sense. But you can ask yourself, can I have a higher level theory in which those are useful concepts? And the answer is certainly yes in principle. You can think of a teleology as a future boundary condition, something toward which it looks like all of the different microstates are trying to evolve. And that picture looks very much like the time reverse of the picture I already showed you. In fact, it literally is, in PowerPoint, just turning the picture upside down. And now there's some small region of particular future conditions toward which your present conditions seem to be evolving. This is no more illegitimate than the one I had on the last picture because it's the same exact kind of underlying thought that relates the two. The question is an empirical one. The question is, when you are actually trying to describe reality at the higher level, is it useful to think in terms of some future goals, some future boundary conditions, some teleology? It may or may not be, but the fact that the standard model and general relativity don't have teleology in them is not an argument against this. And in the practical case, there are arguments in the philosophy of biology. Should we talk about Darwinian natural selection in a language of design and purpose and so forth? And so my point here is just that I see no a priori reason not to, even though the underlying genes being transferred back and forth might not have any goals in mind. If it's a useful, efficient description of reality to have a goal, then by all means, put in the goal. And then if you're a philosopher, you want to know, so okay, if you can talk in the language of teleology or irreversibility, what is real? What actually counts as mattering? Is it just the lower level stuff, or is it anything? And I would, if I were forced to have an answer, I would say that anything counts. So if you have any theory on any level that is by itself a successful theory, then I would be willing to count the fundamental ingredients of that theory as just as real as anything else. So the temperature of the air in this room is not a concept that makes sense at the level of a standard model of particle physics. But I think the temperature is real. I have no trouble saying that it's real. I have no trouble saying that this podium is real or anything like that, even though I don't phrase the definition of the podium in terms of quantum fields at a deep level. So if there is a teleology in some higher level description, I would be happy to say that that is just as real as the quarks and leptons that make it up. After all, I don't believe that the quarks and leptons are themselves the deepest possible level of description. So if I want to say that quarks and leptons are real, I better be able to say that higher level structures are just as real as lower level ones. But honestly, I don't really care. It's just, people do care, so I'm telling you what my opinion would be if I were forced to have an opinion. The kind of issue where people take this seriously is when you talk about free will, for example. Is free will real? Do human beings have free will? So there's clearly some sense in which they don't. If the standard model is true, there is a way of talking about a human being which says, tell me exactly the quantum state of that human being, write down the position and the wave function of every particle in them, and I'm going to use that equation I showed you to evolve them forward in time. There's no element of free will that comes into that description. But that is not the description that anyone ever gives. When you go on a date and you meet someone and they say, tell me about yourself, you don't give them a list of your particles with their wave functions. I'm from Caltech, so at Caltech that would be pretty hot if someone did that. But in the real world, you use coarse-grained macroscopic descriptions. And by my previous argument, those coarse-grained macroscopic vocabulary words refer to things that are just as real as the underlying quarks and leptons. So if it turns out that the best way of talking about human beings is as rational agents that have the ability to make choices, then I would call that ability to make choices just as real as the quarks and leptons that make them up. The problem only comes in, I would argue, when you try to have sentences in them that mix up the different levels. Each level of description is autonomous by itself. It's right or wrong in its own right. The confusions about free will, in my mind, enter in when you say, well, I wake up in the morning, I look in the closet, I'm trying to decide should I wear the red shirt or the blue shirt. But how can I make that decision when it's just my atoms will arrange themselves in such a way as to pick out the red shirt or the blue shirt? The problem with that, so how can I possibly say I have free will? The problem with that description is that in the vocabulary where you are a person making decisions, there's not a separate part which is your atoms moving according to the laws of the standard model. You can either talk the standard model language, in which case you say, I'm just going to solve Schrodinger's equation and figure out the likelihood you'll pick out either shirt, or you can talk the person language, in which case it seems almost inevitable that you will speak a language of making choices and deliberating and using your rationality and your free will. So that is the easy part, free will. Unless you're very uptight about free will, I think relatively speaking, if you buy into the rest of the story, you'd be willing to accept that free will is just as real as anything else. So what about purpose, meaning, and morality? This is where I'm finally getting to the point of the talk. What about these value-laden words that are not conventionally part of science? So there is a temptation that people who are science boosters sometimes give into to say, look, science is awesome. We're going to take all of this fuzzy value talk and ultimately reduce it down to science. I'm going to use science to tell you the difference between right and wrong. This is an ancient tradition of doing this. More recently, E.O. Wilson has pushed this in some sense. Sam Harris has pushed this in some sense. My own personal attitude is that you should resist this temptation very strongly, because it is true that science describes the world, but there are things to do besides describe the world. When it comes to values, we're judging the world and saying that certain things are right and certain things are wrong. That cannot be easily reduced to science. And I don't have time to give a long diatribe about this, but let me give what I think is the best argument for that temptation that I think you should resist. So you say the natural world is all there is. That's the naturalist point of view, which I agree with. And you say, so therefore, all interesting statements are statements about the natural world. Seems plausible, if the natural world is all that exists, that the interesting statements are about that. Science is the correct way of talking about the natural world. I think that that's a defensible proposition. And therefore, all interesting statements are ultimately scientific statements. So the argument would be that if morality is at all interesting, it has to ultimately be based in science. That would be the argument in favor of this point of view. And I think that the loophole here is that science is not the only correct way of talking about the natural world. Science is the right way to describe what happens in the natural world, to tell you, well, if it looks like this now, what will it look like in the future, or what did it look like in the past? But there are ways of talking about the world that go beyond describing it. There are ways of judging the world and assigning values to it, and that is not included in what science actually does. So another way of saying it is, here we go, here are the laws of physics underlying everyday life. Nowhere in here are notions of purpose, meaning, or morality, and you can't fit them in. You cannot shoehorn some idea that human beings should maximally flourish into the underlying laws of nature. But it doesn't mean that notions of right and wrong and value and purpose and meaning don't exist. Just like free will or irreversibility can appear as higher level concepts, so can moral categories appear as higher level concepts. The point is that I keep repeating myself just to make it clear, it's a different kind of way of judging what kind of values you might want to have. So what you need to do when you try to ask yourself, well, what does it mean to be moral? How should we decide what is moral or immoral? Does my life have any meaning or purpose? You have to ask, well, you knew what you were doing when you chose which scientific theory was valid or not. What were you secretly, implicitly doing when you made that choice? And I would argue that you were secretly applying some instrumental rationality. You had a purpose in mind. You had a reason for talking a certain vocabulary rather than talking another vocabulary. That might have been a very basic, simplistic reason. In the case of thermodynamics, you said, look, it's just easier for me to describe what is going on in the room on the basis of the thermodynamics of the air than it would be for me to list every single molecule and its position and its velocity. So I had a very tawdry goal in mind, the simplest possible description that could give me my relevant information. So the same kind of logic can be applied to values and morality, but your goal is something different. Your goal when you come up with a theory of values is not to give the most efficient description of the physical happenings in your environment. And the reason why this is important is because value theories are not fixed by the facts of the world. So we think that it seems to be a feature of physics. We were talking a little bit about this yesterday, but it does not seem to be the case, as far as we know, that given some underlying theory, there are multiple overlying higher level theories that are incompatible with each other but all true. It seems to be that reality appears in a series of nested theories. Theories might look very different but be compatible with each other, but theories cannot be multiple higher level theories that are truly different and yet correspond to the same lower level underlying reality. But when you add values, judgments, evaluations to the mix, then it should be perfectly clear that you can have theories of value that are equally compatible with the underlying physical reality. You have some theory of, me and you, people moving around in the world performing actions, but there seem to be clearly different consistent ways of saying, well, that action is good and that action is bad, and so forth. So there needs to be some criterion for choosing between these different theories of value other than it fits the data in some very basic way. And so I've timed myself very carefully so that I'm running out of time, so I can't tell you how to find the correct theory of value and meaning in the world. But the basis for it, I think, is that we do come into this game with certain goals in mind. Human beings are not blank slates. We have desires, aspirations, emotions, and so forth. So developing a theory of value is different than developing a theory of science, but it's at some level a similar kind of process. The difference is that because the theories of value cannot be fixed by the facts, it's a more creative process in some sense. It is more artistic or poetic. That is the poetic side of poetic naturalism. It's more communicative and more social and more interactive. I think that certain things seem good to me. I know that that's not inherent in the laws of physics or given to me by God. It's just, but I think that some things are nice. Some things I'll be happy when people do them. And I discovered there are other people out there who also think that certain things are good and certain things are not good. And we talk to each other. And we try to both make our internal preferences as logical as they possibly can be. And we try to make our mutual preferences overlap as much as they can. And if somebody disagrees, you say, well, what if someone just refuses to believe your theory of morality that you put forward? Then I would, look at the real world. What actually happens when someone disagrees? We put them in jail, or we go to war, or whatever. We don't sit down and reason with them. If we shared enough, we don't, yes. If we shared enough fundamental values and we thought that they were making a mistake, then we could sit down and reason with them. But there's no rule that says that that has to be the source of error. They could just have different fundamental values, and in which case we can't saying that gay marriage should be illegal is not wrong in the same way that the steady-state theory of cosmology is wrong. There's no observation you could do that could show you why that was incorrect. There's a different kind of social reasoning that has to go into it. So one analogy here, Simon convinced me to use this one last night. Usually I use basketball for this analogy, but Simon says that chess is a better analogy. So the point is, consider the rules of chess in an analogy to the rules of right and wrong. Okay, we invented the laws of chess, right? I don't think most people would not really try to defend a position that you could just integrate out high energy degrees of freedom in the standard model and get the laws of castling, for example. But I think that most people also recognize that the laws of chess are not arbitrary either. It's not, well, they could have been anything, everything is equally good to everything else. Because the point is, when we made up the rules of chess, we had a goal in mind. We wanted to make an entertaining game, interesting, intellectually challenging, and yet rich enough to be interesting, but simple enough to be doable. And the same thing is true with basketball or cricket or whatever you want. You can argue about the rules, you can change them, but and it's not once and for all fixed. You could play a game that was just like chess except with different rules. No one would stop you from playing that game. It just might not fulfill your goals in setting up the game as well. So the motto of this way of thinking comes from Muriel Rukeyser, who is a poet, a very fascinating person in her own right. She wrote a very interesting biography of Gibbs. She came from a chemistry background somehow. And she says the universe is made of stories, not of atoms. And it's a very strange thing for a physicist to be quoting with approval. But the point is that, in one sense, the universe is made of atoms. You can't deny that. But there are other senses in which it's not. There are many, many stories that we can tell about the universe. There's one natural world. There's many ways that we can talk about the natural world. And that is where the poetry and the choice and the creativity comes in. Now that we don't have God anymore, we all took a vote, we agreed, God is not here to give us our notions of right and wrong, but the universe isn't going to give them to us either. We are going to create them, and that process of creation can happen in a way that is perfectly compatible with the underlying physics. We just shouldn't confuse it with the practice of actually doing science. Thank you.